study this chapter is for one dimensional. For one dimensional, we'll introduce the term of pressure. Then for you have to study the static in the two dimensional, where you have to calculate the hydrostatic forces on the plane surfaces, on the curved surfaces. And then we introduce the static for three dimensional. In the three dimensional, we'll introduce you the buoyancy forces, because body must be a three dimensional for a volume to be displaced. So consider here a tank, and the tank is stationary, and we have frame our XYZ axis. Here x and y contribute horizontal plane. So this one is a standard situation in the case of fluid mechanics. As far as z is always perpendicular. That is, regular y direction is our z, is always fixed in the case of fluid mechanics. Consider here one element here in a stationary tank. Since this element is stationary, we can apply the three classical equation of mechanics, that is sigma fx0, sigma fy0 and moment 0. In generalized situation, we will consider here one element of length equal to L, inclined at angle equal to theta, and let assume here that we have a pressure acting from this side equal to P. On the other side, we don't know the pressure is varying or remain constant, so we assume here that the pressure is varying P plus delta P. Don't take this value of delta P as a positive or negative. That we have to prove actually using the standard classical mechanics equation. The weight component is resolved into two parts. One is W sin theta and one is W cos theta. So this vertical component is W cos theta and this component is W sin theta. Now since here element I have taken as the inclined axis, so I will take this axis equal to x axis and this axis equal to y axis. I am taking this axis as the x axis because I have to resolve only one forces. Therefore it is comfortable for me to align the x axis along the longitudinal axis. So if we apply the sigma f along this axis, we will get here this force. Now this axis I have shown upward positive, so this force is positive, is P multiplied by delta A. This force is acting in opposite direction, is P plus delta P, and we have a same cross section area equal to delta A. In addition to this, this component of weight is acting in opposite direction of x, so we have to subtract it, is minus W into sin theta equal to 0. Then W we can replace as the weight component. W is equal to m into g, which is equal to rho into g into volume of this. So volume will be simply equal to delta A multiplied by L. After substitution, we come to know that we have delta P equal to minus rho into g into delta Z. If we put the limit z tend to 0, we get a governing equation here that dP by dz is equal to minus rho g. It means that we do have a pressure change, but the pressure change only takes place along the z direction, and we have the del P by del X equal to 0, del P del Y equal to 0. It clearly indicates that there is no pressure change along the X direction, there is no pressure change along the Y direction. It means that suppose we have a tank here, then the pressure on this level is always remains same. Pressure on this level always remains same. But if the P1 is a pressure here and the P2 is a pressure here, then these two pressure will change. So what we do here is to solve the problem of the pressures, we'll use this concept of dP by dz equal to minus rho g. Minus sign indicate here is that as the z will increase, the pressure will decrease. Consider here one reference level. Above this reference level, it means that our z is positive, and if you move below this reference level, the z will be negative. So this time the z is positive. If this pressure equal to reference pressure equal to P0, then we can calculate this pressure using this concept. As z is increasing, this value become negative. Negative means that the pressure will drop. So we have to write down here P0 with reference to this pressure, and since here z is positive, we'll replace this value as minus rho multiplied by g multiplied by z. But if you move below the reference level, in that case the pressure at this point will be equal to P0, and since here z is decreasing, the P will be increased. We'll write the positive sign. That will be equal to rho multiplied by g multiplied by z. So how much column you have changed, according to that you can do your calculation. Only thing that from time to time you have to change your reference level. From the reference level, if you move above, select negative sign. If you move below the reference line, select positive sign, and reference value plus or minus the product of rho g into h, or the product of rho into g into column of height. Using this technique, we can solve the problem of manometers. So this governing equation has the following characteristic. The changes in pressure correspond to change in the elevation, that is the z direction. If one travels upward in a fluid with a positive z direction, the pressure decreases. So here the pressure is decreases. If one goes downward, that is negative of Z, the pressure increases. Pressure increases by quantity rho g Z. If one moves along the horizontal plane, that is along this plane, in that case the pressure remains constant. The pressure of a fluid always acts perpendicular to the wall in contact. So it is a strict definition of a pressure is force upon area, and the area must be perpendicular. That is the normal stress. Strength of material is same as pressure. The value of the pressure acting at any point in a fluid at rest are equal regardless of its direction. It means that if we consider here any element in the tank, so this element is a basically three-dimensional element, but the pressure acting on this element in any direction remains same. That is, whatever the pressure is along the x direction will be the same as the pressure along the y direction, and the same is the pressure along the z direction. That is, the pressure is a scalar quantity and not a vector quantity. But stress along the x direction will be different, y direction will be different. So stress is a vector quantity and the pressure is a scalar quantity. Equation that you use for calculation of a pressure is rho into g into h. This one is the pressure developed due to liquids. Pressure is equal to weight divided by area. This one is called as the pressure due to the mechanical forces. It is called as mechanical pressure. This one is called as liquid pressure. And the pressure is equal to rho into r into T. This one is called as thermal pressure. So any combination of pressure either we can add or we can subtract, because these are the scalar quantity. Now all this value here, that is this value and this value, is basically a gauge pressure. This one is a gauge pressure. In thermodynamics, we have P equal to rho RT is a absolute pressure. So while addition you have to take that all pressure must be the gauge pressure, all pressure must be either absolute pressure. So we must know what is the relation between the absolute and the gauge pressure. For this one, I have taken the consider here a perfect vacuum where the molecular moment will be equal to 0. If the molecular moment is equal to 0, we have no pressure is acting, because the pressure is due to the molecular activity. If the molecular activity is not present, the pressure will be equal to 0. That is called as perfect volume. From this reference, we have a certain molecular activity that is equal to 760 mm of Hg. That is the surrounding with us. This surrounding has a certain molecular activity. If the molecular activity will increase, it is called as positive gauge. If the molecular activity will decrease, it is called as negative gauge. And if the molecular activity ceases, it is called as perfect vacuum. The reference is taken with respect to the atmospheric for gauge pressure. That is a molecular activity. This is standard molecular activity. So gauge pressure for this one is taken as 0. Any molecular activity will increase, then the atmospheric pressure will be taken as positive gauge. And any molecular activity that decreases in comparison to the atmospheric pressure, it is taken as negative. Now whenever we have a reference with the atmosphere, the term is called as gauge. And if we measure the same value with the perfect vacuum, that is in a thermal, in that case it is called as absolute pressure. So in generalized form, the absolute pressure will be equal to P absolute is equal to P atmospheric plus P gauge. Then whether the P gauge is positive or negative, it depends the molecular activity. So if it is above, you have to take the positive value. If it is below, it is taken as negative value. Number of times the gauge pressure is negative, it is called as suction. The Pascal principle says that if the vessel is closed and the vessel is of a small size, let's consider here that we have one ram and we have second ram of size equal to A1 and size equal to A2. Now since here this level are remain same, so we have a pressure equal to P1 and the pressure equal to P2. Now because of the same level here on the same horizontal level, we have pressure is remain constant, that is P1 and P2 remain constant, because this one is our standard x axis, this one is standard z axis, and this one is standard y axis. Now if we apply here that the force is equal to pressure multiplied by area and the second force equal to A2 multiplied by P2, in that case since P1 and P2 are same, so our force will be get amplified. So we have F1 by A1 equal to F2 by A2. Here we introduce the term called as mechanical advantage, which is output force divided by input force. So input force is F1, output force is F2. This arrangement is commonly used in a hydraulic brake. Advantage is that we have to apply very little force on the pedal, we will get a large force on the brake shoe. and therefore the mechanical advantage will be greater than 1. In this case, you have to remember here that the pressure is given by rho gh, so height restricted here, that it should not be applicable for long columns. Suppose I change the height of this vessel and I shift the ram here, this position, and I say that this height is very large, let's say equal to 2 meter. In that case, we must have a relation between P1 and P2. So this time P1 and P2 will not same. They will be different value because pressure will change. So from this reference, this is at a higher point, so pressure will going to decrease. Same equation dP by dz, which is equal to minus rho times g, can be applied to atmospheric air. For atmospheric air, we have governing equation for air as a PV equal to mRT, because air is modeled as a ideal gas. So ideal gas equation can very well be applied. So we have density equal to mass upon volume, and mass upon volume is same as P by RT. So this substitution we can do in this equation, and we are able to calculate the change in pressure with the change in altitude in the air atmosphere. So we have a sea surface here, and we have a number of spheres on the Earth's surface. We have a troposphere here, which is height equal to 0 to 13.7. Then we have the stratosphere here. This one is a lower stratosphere whose height is range from 13.7 to 16.8. So just remember here, in the case of stratosphere, the temperature is remain constant, and in the case of troposphere, there is a linear variation of temperature. So in the case of troposphere, whose value is equal to 0 to 13.7, the temperature is changed according to the linear law. So suppose we have temperature at the sea level equal to T0, and at any altitude inside the troposphere, if height equal to z, then the temperature in the troposphere is equal to T0 minus lambda times z. This lambda here is called as temperature lapse rate. This equation is only applicable in the case of troposphere, and on an average this value is equal to 6.5 Kelvin per kilometer. It means that if you move vertically by 1 kilometer, the temperature will drop by 6.5. Suppose we take the Mount Everest has a height equal to z equal to, so let approximate equal to 10 kilometer, and on the sea surface we have temperature equal to 300 Kelvin. Then we can very well calculate the temperature on the top of Mount Everest. That will be equal to 300, that is T0 minus 6.5 multiplied by 10, that is 300 minus 65. This is in Kelvin, so that is very close to 235 Kelvin. It's very close to approximately minus 40 degrees Celsius. So quick calculation we can do, but remember here the law is applicable for 13.7 kilometer only. Whereas in the case of lower stratosphere, which is ranging from 13.7 kilometer to 16.8 kilometers, the temperature is remain constant. If the temperature is remain constant here, in that case we have the same derivation you have to use, but you have to keep the temperature constant, and we have to prove this equation. So we have dP by dz will be equal to minus P by RT. So variation is can be done here. Consider here a troposphere whose value maximum value equal to 13.7. At any altitude z, we have temperature equal to T. At sea level we have Z0 equal to 0, that is height equal to 0. Corresponding pressure is P atmospheric, temperature equal to T atmospheric. Since we are using here the ideal gas equation, you have to use this value as the absolute value. That is the pressure you have to take absolute, temperature you have to take in Kelvin. Let assume that the lambda is temperature lapse rate remain constant is 6.5 Kelvin per kilometer. This time we have the governing equation is temperature at any altitude is T is equal to T0 minus lambda z. If I partially differentiate this, I will get dt is equal to T0 is the temperature on the sea surface that remain constant. Lambda is a constant, so we'll get here dz. So rearranging this term, I can replace here dz as dt divided by lambda, and the negative sign will come. And we have a hydrostatic law, which is dP by dz equal to minus rho times g. Rho can be replaced as P by RT. So rearranging this equation and replacing dz as minus dt by lambda, and rho can be replaced as P by RT. We have a variable separation form here. We get a controlling differential equation as dP by dt equal to P into G by R into T by lambda. So since here we have T here, we'll shift dt on the right side and the rest term will be adjusted. So we have dP by P G is a constant value, R is a constant value, lambda is a constant value. R is called as universal gas constant. On the integral we'll get dt by t. Now we have to put the condition at z equal to 0, we have pressure equal to P atmospheric and the corresponding temperature equal to T atmospheric. At any altitude here we are able to calculate the pressure if we know the temperature. Temperature we can calculate using this relation. Now simplify this. The integral of dP by P is natural log and the integral of dt by t is also natural log. So if we find here the final equation we will get here, P upon P atmospheric is equal to T upon T atmospheric to the power 5.26. So this one is a distribution of a pressure. So if you know the pressure at surrounding, that is the atmospheric condition at sea level, temperature at sea level, temperature at the given altitude, we are very much able to calculate what is the pressure on the Mount Everest, because this relation is very well valid up to 13.7 kilometer. This time we have a temperature variation is there, but if we go to the stratosphere, then the temperature will remain constant. The temperature remain constant, then the dt will be equal to 0. Is this hydrostatic law is dp by dz equal to minus rho will be minus p divided by rt divided by g. This time we have to separate the variable for isothermal surface. We can write here dp by p minus g divided by r. Assumption is that temperature remain constant, so we have g r by t remain constant, so we have simply dz, and now you can integrate it. So at z equal to 0, that is on sea surface, we have pressure equal to P atmospheric at any altitude z. But remember here this range is from 13.7 kilometer 13.8 kilometer. Remember like this. So here I have to take this value not equal to 0. I have to take this value as 13.7 kilometer, means outside the troposphere, to 16.8 kilometer. But in fact I will just write here 0 to z for your reference. So this value will be same as ln of p. You will get this value as minus g by rt. This is ln of p divided by P atmospheric, and this time I will simply write equal to z without bothering of this equation. So what I get here is P is equal to P atmospheric, and this entire term after eliminating ln will become e to the power minus g by rt multiplied by z. So what is this law? This one is exponential distribution, because we have e term here and it's a negative exponential. If you want to measure the atmospheric pressure, that can be done with the help of barometer. Barometer is just a inverted tube deep in a mercury tub. So if we have a mercury tub here, this pressure will be equal to same as atmospheric, and as the z value will increase, the pressure will going to drop. So this one is atmospheric pressure, and if you are moving above this side, the pressure will drop. If the pressure will drop, then there is a chance here is that the mercury will boil off. If the mercury will boil off here, some vapor of mercury will be collected. So this one is vapor form here of mercury. All liquids will boil off at low pressure, and since here the height is increasing, the pressure is decreasing. So we are attaining here lower pressure. That pressure is known, that is equal to PV. Then you can start moving from this direction. So this pressure equal to PV. So from this point, that is the reference level, since you are moving downward, you have to write down positive sign. How much column you have changed? You have changed the column equal to rho g h of mercury. Then you come to this level. At this level we have pressure equal to P atmospheric. This fashion we are able to measure using the column of mercury the atmospheric pressure, provided we should know what is the vapor pressure. So in the numerical, if the vapor pressure is not given, that is basically a very low value, you can neglect that quantity, and approximately we have atmospheric pressure equal to rho multiplied by g multiplied by column of mercury. First device is called as piezometer, second device is a U-tube manometer. In this case you have to take the concept of reference, and from reference you have to very quickly move to the point that you are interested. So suppose you are interested to know what is the pressure at point A, and since we are using here fluid, the gauge pressure concept will be applicable. At this point here B, it is open to the atmosphere. So at this point we have PB is equal to P atmospheric, and this pressure in a gauge value will be equal to 0. So therefore I will take this as a reference. Now the pressure at this point is known, so it is called as reference value. Now from this point I want to know the pressure at point A, so I will move vertically downward. If I move vertically downward, it means that I have to select the positive sign. Using this value, I will start with P atmospheric. Since I am moving downward, I will write positive sign. We have rho into G into H, that is a column change, and the rho is the density of this fluid. Where we come, that equal to PA. Now here, if you are interested in the absolute, keep P atmospheric. If you are interested in the gauge, make P atmospheric equal to 0. This time we have a density of this fluid equal to rho 1, and let us assume here that this column here has a different density equal to rho 2, and here we want to know the pressure at point B. So how you start the problem? So first of all you have to see that any standard point is available with us or not. So this leg is open to the atmosphere, so here we have a standard point. So pressure at this point be equal to P atmospheric equal to 0 gauge. Once you make your finalization of the P atmospheric, then you can move from this point to this point. So this one is our x-axis. So pressure at here and the pressure at this point remains same. So it will be same as P atmospheric. From this point, that is from point A, we want to move B. So since from A we want to move towards B, we are moving in a upward direction. So we have P atmospheric, that is the pressure at A. Since we are moving upward, it is a negative pressure, that is a negative sign, and the column change is rho multiplied by G multiplied by H. So this time we have column is of density equal to rho 2, and this level is same, so pressure remains same. Finally we come to point B, so we can comfortably measure the pressure at B. Again we are interested in the absolute, keep P atmospheric. If you are interested in the gauge, then force the value of P atmospheric equal to 0. Now here we have again the same U-tube manometer, and we have given the two columns here. Let's say this liquid has a density equal to rho 2. Let's say this density equal to rho 1. We want to know the pressure at point C. You have to find here that where we have a standard known value. Standard known value is normally a local atmospheric pressure. So this point here will modeled as point A, and this is open to the atmospheric, so this pressure will be equal to 0. From this point you cannot move here. You have to move through the pipe. So you have to check here where the first level is changed. So level change is here. Point B, you have to first move downward here up to B. We are knowing the pressure at A, we can calculate the pressure at B. So we have pressure at B is pressure at A. We are moving downward from A, so it is positive sign. It will be rho multiplied by G. So we have taken this one is rho 2, and the height will be equal to H2. Now so the pressure at B and the pressure at this B prime is remains same. So we have a same pressure here. Now from B prime we want to move upward. If you want to move upward, in that case you have to subtract this quantity. So we have the pressure at C. We are starting from B prime, which is PA plus rho 2 multiplied by G multiplied by H2, and since we are moving upward, it's a minus sign. We have density equal to rho 1. So we have rho 1 multiplied by G multiplied by H1. Finally put PA equal to 0, and you are able to calculate the gauge pressure at point C. Now the inclined tube manometer is normally used for sensitiveness. That is, suppose we have a very small difference in that case we can measure that distance if you make the tube is inclined. So this small distance will be magnified if the angle is made equal to theta. But as far as the calculation is considered here, the value of only dz we are interested, not in incline. The pressure will vary along the z direction only, not along the x and y direction. So we have to consider one point which is open to the atmosphere. So it is measured pressure equal to PA, and this point is open to the atmosphere. So we have a certain vessel here where we want to measure the pressure. In that case we start with the P atmospheric. From this we are moving downwards, so we'll select the positive sign. We have changed the column equal to rho GH. So this column is same as equal to H, which is hypotenuse is S. In that case opposite will be S multiplied by sin theta. In that case we have pressure will be at point A will be equal to rho G S multiplied by sin theta. If we have a vessel here which has a larger cross section equal to A1, and we have a tube connected here which has a smaller cross section. So let's assume here that the well has a diameter equal to D, and this tube has a diameter equal to d. And let us assume here that the well is very large size as compared to the diameter of the tube. This is subjected to the pressure P1 and this is subjected to the pressure P2. Now since here the cross section area is not same, there is a change in the volume takes place. So if this level is dropped by column equal to Z1, in that case this volume will be shifted on the right hand side. So that extra volume will be equal to column equal to Z2 because the diameter is less here. So same volume which has displaced by Z1 is extra displacement will be equal to Z2. And here Z1 is remains same on both sides. Since the volume is constant here, we can very well develop the relation between Z1 and Z2. Simply equate this, obtain relation between Z1 and Z2. Once we develop this relation, then start calculation from P1. So pressure at this point here, now the new level is here. From this new level you have to move upward. So we have P1 is equal to P2 plus Z1 plus Z2. That is this side is Z1 and this side equal to Z2. So total value is Z1 plus Z2 multiplied by rho g. Now here we can replace Z1 in this form. So we have P1 minus P2 equal to rho multiplied by g. Z1 can be replaced as d by capital D whole square multiplied by Z2, and then we can take out Z2 common. If you neglect this dimension here, that is d by d, which one is basically a very small value, then there is an error in the measurement. So this quantity, that is d divided by capital D whole square, basically d divided by capital D is very small value, and again you make a square, that is again a very small value. So even you neglect this one, there is an error. Otherwise we have a direct relation between the two pressures, P1 minus P2 equal to rho g multiplied by Z2. So error is entirely dependent upon the d square divided by capital D square. Adjusting pi by 4, we will say that the error is equal to area A2, that is of the tube, divided by area A1. The pipe is horizontal or pipe is vertical or pipe is inclined. If you consider any 2 points here and you connect a U-tube manometer here, that always measures the piezometric head. So to balance this one, let's assume here that the fluid flow is taking place on the leftward direction. So fluid always move from high pressure to low pressure. So we have pressure equal to P1 and this pressure equal to P2. Let here column height equal to x, which is common to both. Whatever the fluid density here rho, same fluid density in this pipe and the same fluid density here also. Start with P1. From P1 we are moving downward by height equal to x plus hm. Since we are moving downward, we'll write here positive sign. This density equal to rho. Column change is x plus hm multiplied by g. Pressure at this point and the pressure at this point is same, but we have a different density of fluid. So otherwise we can write from this side balance. We have P2 and you are moving downward by column equal to x of density equal to rho. So we have rho g multiplied by x. From this again you are moving downward, so we have rho m into g hm. So we take a balance about this side. One pressure is acting from this right limb and one pressure acting from left limb. If we balance this and solve this, we will get the difference of pressure divided by rho g equal to hm into rho m minus rho multiplied by g divided by rho g. That is called as piezometric head difference. So piezometric head difference is simply hm into rho m by rho minus 1. This one is called as upright manometer. In the case of upright manometer, the manometric fluid density must be greater than the density of working fluid. So you have to use this equation when the fluid density is less as compared to manometric fluid, or we have density of the manometric fluid is more than the density of the working fluid. But if you are using a kerosene and here is a water, or you are using a oil and here is a water, this combination is used for water and mercury, or air and water. This combination is used for the heavier fluid flowing through the pipe and the lighter fluid is in the manometer. So this time again you have to do the same balance, almost same equation you have to do, and finally we'll get here hm. That is the same equation, only these two terms will be get swapped to get the positive answer, because the manometric fluid density is less than the density of working fluid. So this is ratio. This ratio is less than 1. It guaranteed that this is positive value. So this equation and this equation is same. Only care you have to take whether we have inverted position or your upright position. In the upright position, it is rho m by rho minus 1, because rho m is greater than rho. In the inverted position, it is hm into 1 minus rho m by rho. In that case, we have rho m. The video you are watching is from the app, which is the Mode Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.